right, so for part one, our question was to create a model to estimate the percentage of workers whose jobs are currently remote ready for 5 cities, and use the model to predict the percentage of jobs that will be remote ready in 2024 and 2027. So we had a lot more assumptions, but these are the major ones. So number one is workers don't move to these cities and don't change career industries. 2020 and 2021 are significant outliers in the data, so they will not be considered in predicting the long-term trend, which kind of ties to number three, which is the effects of COVID-19 pandemic will be negligible by 2024. The specific job makeup of each broad industry is roughly equal from city to city. And this is not the actual makeup and percentage of the wide industries within a city, it's the specific jobs within each industry. And for number five, the percentage of each specific industry category that is remote ready will not change between 2020 and 2024 and or 2027. And we had to make this is because technological changes are unpredictable. So we're just kind of basing it off of the current technological status quo and like how it's going to go. And we assume that like the trends and the technological changes within each industry is going to be based on the previous years. All right, so for developing the model, we used auto-regressive integrated moving averages model to extrapolate the future industry populations and percentages. And on top of that, since there were like so many industries, like around 10 for each city, there were a lot of original models we needed, right? So in order to make the job easier, we also used a package called PDArima. It's a Python package. And we used a function in it which is called AutoArima to help us find the coefficients which are PDQ for the Arima model. The specific algorithms used by the AutoArima function is KPSS test to find the appropriate number of first differences, and the OCSV test was used to find seasonal unit roots. Here's the general Arima model equation you can see here, which obviously uses the exponential smoothing using moving averages and also the auto-regressive part. So for executing the model, we went a step beyond and didn't just use the normal Arima model, we used the seasonal Arima models. We also had the capital PDQ. So for example, like P is the number of time lags of the auto-regressive model, D is the degrees of differencing, and Q is the order of moving averages. PDQ are the same terms as well, but for the seasonal component. And we also noticed within our data, which we got from the Bureau of Labor Statistics, that when we actually looked at the data, the seasonality was annual, like the patterns repeated annually. So we used M, which is the number of periods in each season, to be 12. And Y, here you can see in the code snippet that Y is the monthly district employment data for each US city. So here are the results and discussions. So here you can see the percentage changes in remote ready proportions for all the industries combined for each of the cities. And you can also see some of the Arima forecasting we did here. We obviously can't go all of them here since there's so many industries. And yeah. So for our strengths and weaknesses, we considered seasonality, which is very important because not only can we look at the overall trends for each year, but we can also potentially predict it monthly. Additionally, our predictions were highly plausible and realistic because we used data straight from the Federal Bureau. And our weaknesses were there was limited data on industries for both British cities. So unfortunately, we could not use the seasonal Arima model for Liverpool and Barrie, and which hindered our ability to use the complex Arima models for them. I'm going to pass it on to Ashley for.
Thank you, Uday. So part two asked us to predict whether individuals who are working in remote ready jobs will actually work from home, because that is a decision that is up to employers and employees, and not everyone who's remote ready will actually work from home. To predict these decisions, we had a few major assumptions. First, we assumed that employees in the computer and mathematical industries were representative of the population of employees in remote ready jobs. We made this assumption because 100% of employees in this industry are remote ready. So as other industries become more and more remote ready, they will approach this industry in certain characteristics. Further, we assume that the opinions of employees in this industry have not changed since 2019 because that was the most current data that we had. Finally, we assumed that employees working from home both chose to and were allowed to by their employers, meaning that we ignored employees that were potentially forced to work from home by their employers or by COVID restrictions. Our source of data was a very large survey from Stack Overflow developers, and such a large survey is conducive to a machine learning model. So that is what we decided to use. Specifically, we decided to use a support vector machine classifier, which can classify individuals into two classes. In this case, it was remote workers and non-remote workers. And it's able to use dozens of input variables, which is also something that our survey had. Further, as a machine learning tool, the SBMC needs both training data and testing data. So we split the survey data into two halves, one for training and one for testing, so that we could actually see how well our machine did on real data. So the way that an SBMC works is that it plots the points from the survey onto a graph in hyperspace. Each variable is considered another dimension. So since we had about a dozen variables, this is a 12-dimensional model, which is impossible to visualize. So this is a two-dimensional drawing of an SBMC. And once the data is divided and plotted like this, what happens is, as you can see in this diagram, the data is projected with a linear transformation into a higher dimension so that a straight line, a hyperplane, can be drawn through the data to divide it evenly. As you can see in 2 dimensions, you can't split that data with a single straight line, but if you transform it into 3 dimensions, you actually can. Our data came from a survey of 90,000 computer and mathematical employees. We can only use 17,000 of those data points, however, because a lot of the data included null values, and the 17,000 points were all of those where every single survey question was answered. Splitting this data into 2 halves, 8,500 each, we used 8,500 training points that were plotted to train the SBMC. Then we tested the SBMC's accuracy using the other 8,500 points. So here's our code, and I would like to hand it off to Uday to explain.
Yeah, so I just wanted to show you, like, since we use scikit-learn, you can see that changing from SVC to any other classifier is super easy. So for instance, we also tried decision trees and logistic regression and many others, and we found that this one worked the best. I also want to make sure is, like, since there was lack of time, we didn't like really fine-tune all the parameters that scikit-learn gives you. For example, here you can see, like, we just ended up using the linear kernel for SVC. But this can obviously be changed to get even better results in the future. And of course, we have the training split, the training and the testing split, the first line, and then, yeah, pretty simple and modular.
Yep. All right, so our results. Our SBMC correctly identified 85% of the testing data. However, we noticed that this was an unbalanced data set. Particularly, there were a lot more non-remote workers than remote workers. And we noticed that the SBMC was better at correctly identifying non-remote workers than correctly identifying remote workers. So when we tried testing the SBMC on a data set that was 50-50 remote and non-remote, it fared a little worse at 71% accuracy. However, that is still decent. So strengths and weaknesses. Our strengths included that SBM models performed very well for large data sets, and our data had about a dozen input variables, so that was a very useful model to use. Further, we used real data for both training and testing. Theoretically, we could have gotten a more accurate model if we used all of the data to train. However, we wouldn't be able to tell you how accurate it was because we wouldn't have any way to test it. Further, our code, as Uday said, was highly modular, which means that if we wanted to include more variables or more data, we very easily could. Finally, the data included questions about employees' working environments, as well as simple demographic data, which allows for a more holistic view of what might inform an employee's decision to work from home. Then we had weaknesses. So our main weakness was that we only used employees in computer and mathematical industries for our data. Now, as more and more industries become remote ready, they should conform and become closer to this industry. However, it's still a weakness to project that onto the entire population. And finally, our model requires input data from all of the survey questions. So we threw out the data that had null values so that we could accurately plot everything in the hyperspace. And that means that a survey has to be fully complete to be predictable. All right, so I will pass this on to Nolan Boucher to describe part 3.
So in part 3, we had to create a model for each first one being that remote work will not impact the rate at which people move into their city. We just made this assumption simply because we assumed that people would move into the city mainly due to work motivations, and that they would move out of the city for other motivations. So people moving into cities for solely work motivations, whereas what our model accounted for. Second, the location that people prefer is not affected by where they currently live. This is just because we assume that other attributes or goals that they have are the sole factors in where they decide to move to, and that their current location of living is not one of those factors. The third assumption is that other than employee age distribution and frequency within household members among the city's workforce, the distribution of additional factors is used in development of the SVM model do not vary significantly between cities. This was mainly made simply to streamline the model, just because this data was not readily available to us. So in developing the model, we used a Monte Carlo simulation to generate a hypothetical population of 1,000 individuals from each city. The individuals that were generated were then given attributes that were generated using the attributes of the entire population of each city, so these individuals would appear as just normal individuals living in the city. And then, on top of that, we each assigned them a remote-ready status, whether they are or they aren't. That was found from the Part 1 agreement model. Once we had our subset of remote-ready individuals out of our total of 1,000, we then ran these remote-ready individuals through the SVMC Part 2 to determine whether they would actually work remotely or not. And then once we had our remote-ready individuals who had decided to work remotely, we then used several factors to decide how they would be most impacting the cities that they were moving into or out of. These factors being business operating costs and office space and CO2 emissions from transportation. We decided that 26% of all these workers who would be moving would actually decide to move if they were considering to move, due to this just being the national average. That the average cost of office space for a single employee is $1,450, and that cost would be cut from a business's operating costs if that worker went online, and that the average emissions of a passenger vehicle was 404 grams of CO2 per mile on average, and that cost would be cut if an employee decided to work online and no longer had to take transportation to work. Here is another code snippet from this one.
Yeah, so this is the basic template we use for each city. So here you can see that our initial value is 1,000, which we're going to run the Monte Carlo simulation on. And then industry distribution and remote distributions, those vary obviously depending upon the city. And then we randomly assign people while keeping in accord with the distributions, whether they're not remote ready or not for each city. And then we also use the demographic factors, the general distribution demographic factors for each city, to assign them some of the factors for the SVMC model. And then once we have given those factors, depending upon the city, we can find out whether or not a person will be is going to go remote. We also keep track of the total CO2 emissions and money saved to get our final answer.
So for our results and discussion, we decided that the rate that each city would be ranked from 1 to 5 on how they were most impacted by cost of maintenance and CO2 avoided. Obviously, I won't go through how each city was ranked on every level, but you can see there the 1 to 5 scale, as well as the percentages of total remote workers in a city for each city in 2024 and 2027. Now, for our strengths and weaknesses, the model was again accounted for uncertainty and many possibilities. One of the main weaknesses was that it did not have many independent variables that were taken in to determine whether an individual would or would not move. However, the code is highly modular and can easily account for more of these variables were we to add them in the future. And again, the demographic distributions often vary within industries, but we do not account for this. But again, because the code is modular, it could be further adapted to in the future. Thank you for having us. Thank you.
question. So my question is about your solution for the first question in your paper. So you have a model that provides a really detailed approximation of the number of jobs, and you used moving average approach. I'm just wondering if you can comment on how do you think your results, the prediction that you got would be different than something simple like a regression model.
So a rainbow model is, so it also keeps track of seasonality, and of course, it's not just first difference you retain, right? Like in a normal class, you'll like the first rainbow model you learn is the first difference. But since we're using AutoRima, it can go like up to 5 or 6 difference, which can like detect obviously more complicated patterns.
I think those more complicated patterns have an impact on how that model like affected your question 2 answer, for example. Like how does seasonality impact your final solution for the problem?
The seasonality, well, I didn't really look into the specifics for why it did.
Well, with a simpler regression model, whether it's linear or polynomial, the linear regression models aren't great at making very precise predictions, and they would just sort of keep going up forever. And then the polynomial models, while they're good at interpolating, they are really bad at extrapolating. So this model was good in that it was actually able to maintain these details in a prediction. And I just think that lended to a more accurate result.
I wanted to ask about the assumption that you made when you decided to focus on the computer science and math sector. So I think the idea was that since that is sort of at the leading edge of remote ready, then everything would maybe be moving toward that. But is that really true of all industries? I'm thinking of other teams that pointed out logging and mining probably are not moving that direction. So could you talk about the impacts of that decision?
Right, so this decision, the SVMC model only looked at people that were already remote ready. So in logging and mining, you're going to have 95% that aren't remote ready, but the 5% that are probably going to be a bit more similar to computer and mathematical. So like, yeah, someone who's actually working, cutting down trees or actually mining, they'll be pretty different, but perhaps an analyst who is researching different areas, different land claims, their job is already a lot on the computer. So we assume that they might have more similar attributes to computer and mathematical.
Yeah, I just want to add to that is when we were looking at the actual data provided by the entry challenge, it was like for within each specific industry, how many are remote ready, right? And since the problem is asking about out of the people who are remote ready, how many will actually know? I think if we had the choice between all the industries, computer and mathematics would be the best because in the data you were given, it was around 99% or something, which could be transferred over. So optimally, we would be looking at a population sample of all the industries and how many of them are remote ready. Unfortunately, this was the best survey we could find, but I think this is still a pretty good assumption. It can't be applied to the remote ready.
Okay, thank you. I have a question about how you address question 3. You did your Monte Carlo simulation. You generated individuals. Could you say a little bit more about what characteristics you used and how you generate random values for those characteristics when you made your population?
Sure. So first of all, when you have an individual, right? We use the NumPy to since we had a discrete distribution for each industry, it was like 10% for mining or 20% for computer. We ran this to like randomly get which industry an individual is working in, and then after that we applied the numbers we have from our question 1, which is like percentages of how many will be remote ready, to again determine whether that individual will be remote ready. And then for the actual factors for the SVMC, we used a lot of distributions for each of the factors. So right, we had around like 12 factors for the support vector we had general distributions for each of those factors. Additionally, for the age and I think the amount of children you have, that was determined, that was city-specific distributions. So we used those to get the final factors, like the characteristics of that.
I think that's all we have time for, but thank you so much.